Good afternoon, good morning, everyone. Welcome to the first session in the track of data science and discrete mathematics. So we will have 4 talks, and the first one will be by Bubacarr and Samuel Mensah, and it's exploring applications of mathematics in data science. Welcome, Bubacarr.
Yeah, good. It's still morning, right? Good morning, everyone, once again. I basically said what I wanted to say. The idea is just to introduce the session, and the goal of most of the work I was doing is around exploring the using of applied math in data science. And so when I was appointed as chair for mathematics of data science. I have this applied math and computational math background, and I want to consider the work I do being the span of the whole space of applied mathematics. So the talks that would be given, Samuel will give a talk on the diabetic retinopathy I spoke about. Samuel was my first PhD student. He just graduated last year. So I think that would kind of summarize some of the work we have done there. And then we will have some collaborations with some other guys that would also speak. In fact, I think I have a slide. Yeah, so there's this slide where I try to explain the spectrum of applied mathematics. You have people doing theory and modeling, computations, and real-world applications. And so we have projects that span the space, like this non-negative signal recovery and algorithm unfolding that Peter will talk about. We worked with some students on this together. And we have some works on PINs, physics-informed machine learning, like PINs and the HCNN, historically consistent neural networks, which has both the design of the algorithms and analyzing the theory around them, but also applications. We are applying them like the HCNN. We are applying to predicting wind output, for instance, or wind speeds, which is necessary for predicting renewable energies. Then we have some other theoretical work in spanning again this space on wavelets, matrix learning, and equation learning, which we work with these students on. And we have Maxime, who's going to give a talk. There will be a talk on this convergence of stochastic gradient descent. And Samuel's work is on this diabetic retinopathy. And we have many other students worked on different applications of these tools. So that's just what I wanted to share with you and say I would let Samuel give a talk instead of me. And then Peter will talk about this non-negative matrix problem, non-negative signal problem. And we have Sabrine talking about some of this work in this space. And the last one will be Maxime. So we have these 4 talks coming, okay? All right, Samuel, well, welcome. You can start the second talk.
Okay. Hi, everyone. My name is Samuel, and as Bubacarr said, I did my PhD with Bubacarr, and my PhD was mostly on analyzing retinal fundus images with deep learning models. So I will start by introducing the talk and also talk about diabetic retinopathy classification. Then we also talk about predicting cardiovascular risk factors. Then we also show some other work we did on CNNs and vision transformers. Then I'll summarize. So I'll start with a retina. So in this image we have a healthy retina image. Okay, and the most important part of a retina is the fovea. This region is where images fall onto for us to see as human beings, and these are usually electric signals which are sent to the optic disc. And the optic disc transfer them to the brain for interpretation. Then we have the blood vessels. So we have another image here, which is an example of a diseased retinal image. And we see that there are some abnormalities over here, over this region, and yeah. So there are some diseases that affect retinal images, and we have diabetic retinopathy, we have some cardiovascular diseases. Also, there are age macular degeneration and retinal detachment and so on. But for this talk, we would look at only diabetic retinopathy and cardiovascular diseases. So the diabetic retinopathy, we have 5 main classes. We have the normal class, we have mild, moderate, severe, and PDR. PDR stands for proliferative diabetic retinopathy. And these are classified based on the number of lesions. So this is a lesion, so the number of lesions that are appearing in the retina. So for example, we see that this has a lot of lesions in here, so it's classified as severe. And this also have some other further lesions as well, and it's classified as PDR. By the way, this data set is classified by the specialists or clinicians. And we also have the cardiovascular disease. So for cardiovascular disease, we typically have some risk factors which contribute for one to say this is a cardiovascular disease. And some of these risk factors include age, sex, smoking status, and so on. But in this data set, we only had access to age, sex, and hypertension status. So that is the only risk factors that we used. Then we look at our motivation. So there are a lot of eye issues related to the retina, but there are just a few ophthalmologists available. So our approach was to come up with deep learning models to help resolve this issue. Then there are also issue of subjective diagnosis. So sometimes maybe clinician, one would say this particular image contains diseased image. Another clinician will say it doesn't contain a diseased image. So there are sometimes subjective diagnoses. And this is why we try to use deep learning to solve these problems. And this image, I got it from this paper here, and it's by Google, and they did a study which showed that when or before AI, the evaluation of diagnosis typically took between 2 to 10 weeks, but with deep learning or AI, it can only take 10 minutes. So our aims were to, first of all, classify and localize lesions in diabetic retinopathy, then also build a multi-task model or learning model to predict cardiovascular risk factors, which I mentioned earlier on, and to also propose benefits of using hybrid models, which I'll talk about later. So our approach was first to use transfer learning, and transfer learning basically takes in a source data, so it can be natural images, for example, images containing cars, animals, and different things. You feed it to a model, and you get the knowledge. Then we create a new model, train this new model, but using the knowledge obtained from this model that has already been trained. And we feed it with a new data set, which in this case is the retina images, to get a new, or to classify them, the data set. So I'm going to talk about how we localize the lesions, and we do that using an approach called gradient-weighted class activation mapping. And first of all, we extract feature maps from the model that we have trained, and we obtain gradients of the feature maps that we have extracted from the model. So we first of all train the model, classify it, and for each class we obtain gradients for it. And these gradients are obtained with respect to the feature map that has been extracted. So we call these the neuron important weight, and after obtaining the neuron important weight, we weight them with the feature maps. Then we apply ReLU on top of it, just to get only the positive values. So after getting this ReLU, or applying the ReLU on it, we now overlay the obtained feature maps on top of the image. So I will just show you in the next image. So we have here the image passing through a CNN backbone. We obtain the feature maps here. This feature map is used for classification, as we see over here. Then this feature map is now used to obtain the neuron important weight. Then it is fed to ReLU. Then we get this matrix, which contains the heat map. And this heat map is now overlaid on top of the input to get this overlaid image. So we can see that in this example, the heat map has been overlaid on top of the lesions. So we see there are some lesions over here, and there are some heat maps that has been generated on top of it. So the data set that we used is called APTOS, which stands for Asian Pacific Teleoptometry. So this data set has already been classified, as I showed earlier on. So normal means healthy. Then we have mild, moderate, severe, and PDR. And in this example, we only had 3,662 examples of them. Then we do a pre-processing and augmentation. So for pre-processing, we did resizing. We resized all the data sets, and we applied an approach called CLAHI, which is contrast limited adaptive histogram equalization. Then we augmented the data set by random flipping, rotation, and color jittering the images. The CNN backbone that we used were VGG16, ResNet 50, Inception V3, and Inception ResNet version 2. So we immediately got some results, and we first of all just wanted to see, when we do a random, or when we train the model from scratch, how does it perform against when we feed it to a pre-trained model. And we see that already the pre-trained models have very good results compared to when we train them from scratch. Here, I just wanted to show the importance of CLAHI. So when we apply the CLAHI, we see that the results is far better than when we didn't apply the CLAHI. So for example, when we look at the ResNet, which had the best performance among all the other models, we see that it had 97.4%, and that outperforms every other model that was trained here. And when we also look at, after training, we generated the heat maps again for the various classes, and we see that the heat maps are correctly overlaying on top of the lesions. So I would explain or look at this particular example. We see that there are some lesions over here, and the heat maps is localizing it. For the mild, we see that there is also a very tiny lesion over here, and the heat map has, or the model has kind of selected this area, saying that this part is important. And we also look at see that the confidences that have been generated for the predictions are quite high as well. Okay. So in summary, we classified diabetic retinopathy. Then we saw that the best performing model in this case was the ResNet 50. Then we localized the lesions using the GradCam 15. So for the rest of the talk, we used ResNet 50 for our experiments. So for cardiovascular risk factors, we had, as I mentioned earlier on, we used age, sex, and hypertension. We used them only because the remaining risk factors had missing info, a lot of missing info, so we had to stick to these three. So with this, we built a multi-task classification model to predict them. So the approach was to feed a retina model, again through a pre-processing and augmentation model technique. Then we have a model sharing technique, then we predict them. So for the predictions, we had classification for sex and hypertension. So in that case, we had whether the individual or the image belongs to a male or a female, and for hypertension, whether the person has hypertension or not. Then we have regression for the age because the values were not categorized. So our approach were to compare two examples or two main approaches in this kind of problems. So it is a multi-task learning problem, and multi-task learning problems, we can either use a hard parameter sharing. That is, we have an input which passes through these techniques. Then the model is just used to extract one feature or feature map, and then we use it for the predictions. But for a soft sharing parameter, each task would have its own feature extractor, and then we predict them accordingly. And we have this blank space here, which basically stands for a custom block, which is an adaptive pooling and a linear layer. So in this experiment, we also use the IPAX dataset, and again, the Resonance 50 backbone. And the dataset had various fields labeled as field 1, field 2, and field 3. So for field 1 has both the optic disc and the fovea showing in the center of the image. For field 2, only the optic disc shows in the image, and for field 3, only the fovea shows. In this example, it's not showing so well, but it's seen over here. And in total, there were 476,000 images. So we now compared the results, and we find that the performance are quite similar to each other. So we have STL, which is single task learning. That is, we try to just build a model that would only predict any of these tasks at a go. And then we have the MTL, which is the multi-task learning HPS, that is hard parameter sharing. We trained this model just to predict the tasks at the same time with these two approaches. So we compare the results, and we see for these two results, we see that the HPS performs better than the SPS. When we compare it against when we trained it individually, we see that it is quite similar. But then we get the advantage of training it within a short period of time than training this individually, which would take 3 times as much as the time trained. So also we show some results for that. And we have 4 random examples, and for each one of them we have the ground truth, and we have their corresponding predictions. So for age, we see that the HPS has 65. Age in this case we have 67. The individual is 67 years old, and the HPS model predicted 65.95 years, which is quite close. The SPS is a bit off, but then when it looks like the sex and the hypertension, the model got them correct. And it's similar for the other examples as well. We see that the model struggled, especially with the SPS, to predict the age. But for the other tasks, the model was okay with it. So when we localized some images, we saw that the model always, when the prediction is a male prediction, it always looks at the optic disc, or it highlights the optic disc when it is a male prediction. When it is a female prediction, the model highlights the fovea, or it highlights both the fovea and the optic disc. So these are correct predictions. So we just wanted to see how it is when we predict for incorrect, or when we get an incorrect prediction. So in this example, the original or the ground truth for this image is a female, but the model predicted it as male, and we see that the corresponding heat map is on top of the optic disc. And in this case as well, the ground truth are female, but it predicted it as, sorry, the ground truth is male, but predicted them as female, and we see that it's looking at either the foveae or the foveae and the optic disc at the same time. So if you remember, I showed some other fields as well. So we wanted to see if the other fields also can give us some good results, but unfortunately the results is not as good when we use the field one, which also indicates that both the, when we have images showing both the field one, showing both the optic disc and the foveae, it is better for prediction. So I'll just skip this one and then quickly come to this. So we have another technique that we came up with. So we have another ResNet 50 model, but we modified it by getting feature maps out of each block here, and we applied a technique called fully convolutional transformer for prediction. So instead of doing the normal ResNet 50 of passing an image through the various blocks to get a classification, we didn't do that, but we extract the feature maps from each block and concatenated the output from fully convolutional transformer for prediction. And this is how the fully convolutional transformer looks like. It is a transformer model which takes in convolutional patch embeddings to this particular layer, which is also just convolutions, and then we combine them using a multi-head self-attention, and then we normalize them at the end. And this is what we got. And we compare them to other models. So this, by the way, was done because we wanted to have a model that has attention in it. And these are other attention models, and when we compare them, this is our model. We didn't get the best performing output, but we see that it's the second performing, or it is best compared to the other ones. The best performing model was the swing model, which had an accuracy of 97.53, but we got 97.46, which was the second best performing model. So we also did some visualization again, and this is quite, it's very small. You can't see the details, but this is again our model, and we see that it kind of concentrates again on the lesions. So in summary, we explored different attention model. We proposed a hybrid model with, which also performed on par with, some text is missing, but with fewer parameters. That is what I meant to say over here. I'll skip this one. So currently, so all these that I talked about were post-hoc attention techniques, which you get the attention after you have trained the models, but then currently I'm working as a postdoc, and we build models that has attention already inside the model, and here are some examples that I wanted to show regarding that. Okay, so thank you.
Thank you very much, Samuel. Maybe we have time for one question.
Thank you for such a nice presentation. You said in your in your summary that you want in your hybrid model that you are supposed to use what do you call this? Fewer parameters. Yeah. There, where you said we propose the hybrid model. What is the significance of having a model that captures fewer parameters?
So when you have a model with few parameters, it's always advantageous, especially during training. So your model doesn't use a lot of, for example, GPU memory. It also trains faster, and so basically, if you have fewer parameters, your model is a cheap model, and you don't need. Typically, we want to build a model that is not expensive. So that is when you have a model with fewer parameters, it is a good thing. Yeah.
Okay. Don't you have a risk of losing some important parameters in there?
So the idea is not to build a model with a lot of parameters. It's possible that you may lose some important features, but I think the whole idea is to provide a summary, not to make your model too complicated. So it's better to have models with fewer parameters. Yeah.
Oh, thank you.
Yeah, you're welcome.
Thank you for your nice presentation.
Yeah.
You say that for your postdoc you are working on a model based on the attention-based model, right?
Yes.
Yeah, yeah. I didn't get well. Why attention?
Yeah. The reason why we consider attention is models have been considered as, or deep learning models especially, have been considered black box. And we sometimes want to get some interpretations for the models that we have trained. And this is when attention come in. And also, attention can also serve as a guide for the model to look at important regions of the data, for example. So this is why we always look at attention. Yeah.
Thank you.
Okay, since we are a little late, I'm going to say let's take other questions offline. Thank you again, Samuel.